So in this short presentation, I will talk a little bit about the dynamics of neutron star tides. I will try to introduce the problem and talk a little bit about some of the progress we're making at the moment. So to set the scene, let's think a little bit about when the tide comes into play in a binary neutron star in spiral. So this is the usual frequency strain plot, and we know that if we start off far apart for a separated binary, the two masses are effectively point particle. The in spiral is described by post-Newtonian expansions. If we go to the merger itself, then clearly we require full nonlinear numerical relativity simulations, but in between there is a binary separations from something like 100 Hertz or so up to merger, where the neutron stars get increasingly stretched by the tidal interaction with the companion, where we can analyze the problem through perturbation theory, and where the answer depends to some extent on the deformability of the matter. So this gives us, through gravitational wave astronomy, an avenue for probing the matter at extreme pressures and densities associated with neutron star cores. Now, this diagram from Jocelyn Reed I think is really good, because it also gives us roughly a description of what happened in GW 1708-17, the first observed neutron star binary merger, where you can see that the in-spiral part is kind of detectable, but the merger itself is not. Now, if we look at what was achieved, so here's from the 1708-17 detection paper, in terms of the two tidal deformabilities called lambda here, you see that this is a region that's allowed, here's a region that's excluded. The curves MS1, MS1b, for example, are examples of equations of state that lead to neutron stars too large to be allowed by this observation. Now the lambda, the tidal deformability, is essentially how much the matter is deformed by the impact of a given tidal field. And that's typically either written as lambda, the tidal deformability, or expressed in something called the love number K2, where there's a radius scaling, radius to the fifth power going between these two. So far so good. The one thing to note is that the love numbers, or the tidal deformability, was not observed in 1708-17, but constrained. So in terms of neutron star mass and radius, the mass is fairly well measured by the observation, but the radius slightly less so. So the tidal deformability constrains the radius, and here's a typical indicative illustration of that in the mass radius diagram. So 1708-17 roughly constrains the neutron star radius to something like 10 to 13 and a bit kilometers. It overlays pretty well with the expectations from theory, which I've shown as a pink band. That's the error bars from a model from Carroll effective field theory. The blue region is from estimates for a range of accreting neutron stars. 1708-17, the red region, which is from the LIGO observation, also is quite similar to the constraints obtained from NICER recently. So this is roughly what we think we know about neutron star radii at the moment. So one question you might ask is, what happens to all the gory neutron star physics? The fact that we should have an elastic crust, we've got a superfluid core, maybe a deconfined quarks and all that stuff. Where does that sit in this problem? Well, the answer, I think, is that we need to go beyond the static tide, the love number, and the tidal deformability that I've mentioned so far, and think about the dynamics. So that leads us on to questions about the dynamical tide. So what does that mean? Well, one thing that happens as the binary spirals together is that individual oscillation modes in the stellar fluid might become resonant, so resonantly driven by the tidal field, and that leads to them growing in amplitude and perhaps impacting on the gravitational wave phasing. The typical modes that come into play during a binary in spiral are called gravity modes. They are due to the fact that the matter composition changes as you go from low densities to higher densities, and the fact that as you distort the matter, the nuclear reactions are too slow to reinstate an equilibrium in the matter. Another oscillation mode that comes into play is the fundamental F mode, which interacts the strongest with the tides, basically because it looks the closest to the tidal deformation, but it is fairly high frequency, a couple of kilohertz, so it might not become resonant until after merger. Still, as I'll show in a minute, this turns out to be the strongest tidal interaction, the strongest contribution to the dynamical tide. Then there's been suggestions that nonlinear coupling between the pressure P modes and these G modes that I mentioned might actually be, when coupled to the tide, unstable at some point during the in-spiral. If that were to be the case, then that could have a drastic impact on the gravitational wave phasing. However, the fact that this was not observed in the case of 1708-17 suggests that maybe this mechanism is much weaker than has been suggested. And then we have other parts of the physics like the elastic crust. Calculations suggest that this leaves a small imprint on the tidal signal, which one might expect because the crust is fairly wobbly. We have the superfluid interior, which will impact on these issues through shifting the oscillation mode frequencies around and making the composition come into play in a different way. So this problem now is very complicated, but in principle, the sort of leading order solution is quite simple, because what happens is, if you look at the excitation of the individual modes, so here's an example from a work in progress that I'm doing with Andrea Passamonti in Rome. What we're showing here is the dimensionless energy deposited in a mode at a given binary separation in tens of kilometers. So here we're at 200 kilometers, the merger is somewhere at 2, so somewhere at 20, so somewhere down here. And you see that by far the strongest excited mode is the fundamental F mode, simply because its closest resembles the tidal driving. And then we have a family of gravity G modes due to the composition that come into play at some 100 kilometers and closer. Fundamental mode, or the leading G mode, and overtones, they tend to be more and more weakly excited, simply because of the nature of these modes. And the leading G mode, you can see it differs to the F mode by about 1%. So the G mode composition effects impact on the tide at the 1% level, give or take. Then I have two features that are associated with the neutron star crust. So the outer 1 kilometer or so of the neutron star that is elastic, I have the shear oscillations in the crust, which are called S1, S2, S3 here, which is how the crust itself oscillates. You see, this is a feature that's even weaker than the G mode, so it's probably irrelevant from all observational points of view, but conceptually it's still important. And then we have a feature here that comes in at very early on, several hundred kilometers separation, which is called the interface mode, which exists simply because there is a transition between fluid to elastic regions in this star. Again, you can see that that's enters at roughly the 1% level of the fundamental mode excitation, so roughly 1% of the dynamical tide is in this particular mode resonance. So clearly this is one example for a particularly simple neutron star equation of state model and so on, but it gives us an illustration of the fact that if we're interested in issues to do with the composition and state of matter in the neutron star interior, we need to be able to detect features at the 1% level or couple of percent level in the tidal response. Now, what we can do is we can play games with that and ask, well, suppose I don't really care about 1% corrections, but I focus on the F mode, so I focus on this F mode excitation here, then how well can I do compared to numerical relativity simulations? So here's an example, again, with another set of work done with Pantenis Pnigoras, again, also in Rome, where we've taken the full set of modes, thrown everything away apart from the fundamental mode, and then played a couple of games where we say that we're going to now make this expression, which happens to come from Newtonian gravity, kind of relativistic by using what's called a universal relation that links the frequency of the mode to the tidal deformability in the first place, and then approximating the gravitational redshift which comes into play in relativity, as well as the rotational frame dragging that enters because you got a binary orbit. Now, if you play that game, then you can get an approximate expression for how the effective tidal deformability, say an effective love number, changes with orbital frequency. The orbital frequency here is omega, as we spiral towards merger, where this colored region is beyond merger. Now, I'm comparing the gray bands, which comes from this simple formula that were written down, to expressions from Jan Steinhoff and Tanja Hinderer and others from a couple of years ago with a more elaborate analysis, the blue and the red curves. You can see that for particular values, this approximate gray band overlays very nicely this blue and red regions up to very close to merger, where you have to account for the fact that you don't go singular at the resonance and things like that, which we took to be in the fine print. So that shows that this approximation works very well compared to the only other similar calculation in the literature. And then you can say, well, okay, so how well can I do compared to full-blown numerical relativity? So that's in the right-hand panel. Here we're showing the changes in orbital gravitational wave phasing. So the tidal contribution to the gravitational wave phasing, the derivative of that with respect to the post-Newtonian expansion parameter. So it's just a different representation of the orbital frequency. The merger here happens at something like 0.11, 0.12 in this parameter. I'm showing the black curve is a numerical simulation by Tim Dietrich's group. So it's the most recent calculation of this kind. And then a fit to this simulation for the very last sets of orbits to a post-Newtonian expansion down here for very low frequencies. And then I'm showing the blue curve here is the tidal response if we ignore the dynamical contribution. The red curve corresponds to actually the blue curve over here on the left. What happens if we take the F mode excitation and we model it the same way as we did over here? And you see that it does a little bit better than the calculation without this dynamical contribution, but it's not great compared to numerical relativity. And then the dashed red curve says, well, I'm going to go hell for leather and just assume that I'm free to play with the one parameter this model has, and you see that then I can write down a simple expression that lasts almost all the way up to merger compared to the numerical relativity fit. So that's a very good comparison. Actually, it stays accurate to less than a couple of % in orbital phasing all the way up to very close to merger. So that, I think, illustrates how the dynamical tide does come into play, what the main features are, and that we can write down simple approximations that compare very well to simulations. So that's pretty much it. What's the take-home message? Well, as we improve the sensitivity of interferometers, we're beginning to constrain neutron star theory. But if we really want to dig deeper into the physics, then we probably need third generation instruments where we expect to be able to observe, in lucky, fortunate cases, things like the tidal deformability and the love number with a precision of maybe a few %, which is where these effects I've talked about come into play. The dynamical tide, I think, is a good benchmark for these kinds of problems, in particular in the sense that the physics we add is not leading order. It does not dominate the signal. but it can possibly be extracted from high signal to noise events. And it sets a kind of systematic error floor that we need to account for, need to be able to account for. We need to make sure that this is not above the noise level, say, in the detection. In particular, then, this dynamical tide associated with the fundamental F mode enhances the tidal response, in fact significantly so, close to merger, and clearly is something that we need to account for in data analysis work on neutron star binaries. So that's it. Thank you very much.